Hello everybody, my name is Maggie Ha. My research mentor is Dr. Gonu from Department of Mathematics and Statistics at University of Houston downtown. The topic is about abstract algebra and the title is Harmonic symmetry of the regular n-gon multi-sided equal length shape are even. Next please. Here is the outline of my presentation today. Next please. Group theory is the first topic of abstract algebra. It studies the symmetry, the transformation, and the structure in mathematical system. Although group theory is abstract by nature, it has a huge application in many areas beyond mathematical field, including chemistry, physics, cryptography, and computer science. When we're talking about group, we often differentiate between commutative or abelian group with non-abelian group or non-commutative group. So, out of the non-abelian group, the dihero group Dn is one of the first non-abelian groups students often encounter during the first course of abstract algebra. Understanding the dihero group can help build a solid foundation for more advanced abstract concepts in abstract algebra. When we study group, we often interested in finding the subgroup, especially subgroup of index 2, because all of the subgroup of index 2 is normal. So it is known that there is only one subgroup of index 2 when n is odd and three subgroups of index 2 when n is even. By counting the number of even symmetry in dihero group, we can eventually find explicitly all the subgroup of index 2 in Dn. Next please. Here is some background for Dn. Here are some examples of regular n-gon. We have the triangle, square, pentagon. And what I mean by a symmetry in an action of movement we take on a regular n-gon, and if this action results in a same regular n-gon with the same orientation in space, we call it a symmetry. So for example, if we rotate the triangle a degree 120 degrees counterclockwise, we have a symmetry. If we take a reflection across the string line, we have another symmetry. Can you press enter so I have the, okay. But if we just take a rotation of 60 degrees counterclockwise, we do not have a symmetry because the dashed line triangle is not the same orientation as the first triangle. Next please. So in the dihero group Dn, we have, actually there are two types of symmetry, rotation and reflection. And in Dn, it takes n rotation and n reflection as element. And the operation in Dn is composition. Next please. When n is even, we have two types of reflection because we have two types of reflection line. The first line comes across two opposite vertex of the regular n-gon, and the second line, the second type of the reflection line comes across two midpoint of two opposite edges. When n is odd, I have only one reflection because there is only one type of reflection line. This line coming through one vertex and the midpoint of the opposite edge. So any reflection is either a chain rotation or a product of the chain rotation, and any rotation is the value of the n cycle 1 to n. Here is the characteristic of the operation in Dn. The product of two rotation is a rotation. A product of two reflection is a rotation. But the product of a reflection and a rotation in any direction is a reflection. Next please. We already know that the alternating group A sub n is the group that contains all the even permutation, and the dihero group Dn is the group that contains all the symmetry. So by counting the number of this intersection, we're going to have the number of even symmetry in Dn. Next please. So for the method, in this project, I need to rule and I want to rule default theorem. I'm going to go through it one by one. Next, please. I have two cases. The first case is any arc, I have theorem 1. And the second case when any even, I use theorem 2 and theorem 3. And for the result, I have theorem 4. Next, please. Theorem 1 is the simplest one. For the case when any arc, the cyclic subgroup generated by the n cycle 1 to n is the only subgroup of order n in the n. It is obvious to see because any cyclic subgroup generated by any element in the group is the subgroup itself, and because it is the n cycle, the order must be n, and it actually the subgroup of order rotation in the n. Next, please. For the theorem 2, this is for the case when n is even. I want to prove that the even rotation of the n are exactly the element in this cyclic subgroup. And I will treat the theorem like an if and only if problem. That means I have to go in the forward direction and backward direction. For the forward direction, I want to rule all the elements in this subgroup are even rotation. And in the backward direction, I want to rule any even rotation is a power of the product of the 2 n over 2 cycle. Next, please. For theorem 3, it's still for the case when n is even. I want to rule the following as the subgroup of order n in the n. For the subgroup number 1, it's kind of similar to theorem 1, so I'm going to skip it. For number 2 and number 3, I have some notation. The first one is ER sub n. ER sub n is the set of all the even reflection in the n, and OR sub n is the set of all the arc reflection in the n. So I have group the n at this oval shape. I divide it into 4. The vertical line divided the dihedral group into rotation and reflection, and the horizontal line divided the dihedral group into even and arc. So in the corner, I have even reflection, and down here I have arc reflection. So in order to rule number 2 and number 3, I have to use 3-step test to check if it's really a subgroup in the n. And the next step, I want to count the element of ER sub n and the number of elements in ER sub n and number of elements in OR sub n. Actually, I don't have time to show you how I count it, but the result is that the number of elements in ER sub n equal to the number of elements in OR sub n and equal to n sub n. And that's why the order of number 2 and number 3 is n sub n plus n sub n en, and similar to number 3. Next slide, please. And here is the result. For the result, I use theorem 4. For the case when n is even, I have the number of even symmetry in en. For the case when n is odd, I have 2 smaller k. In the case, when we divided n by 4, if we have the remainder in 3, in this case, the number of even symmetry in the n is n. But if we take n divided by 4 and we get the remainder at 1, the number of the even symmetry in the n is 2n. Next, please. So here is my reference for my project. Next, please. And look at the end of my presentation. Thank you, and